Joseph Mikett. I'm the Director of Climate Policy here at the Niskanen Center, and we're very happy that you are all joining us today to learn a little bit about climate change and wildfires. We selected this topic because, let's see here, share screen. We selected this topic because every summer, there tend to be large wildfires here in the United States, particularly in the Western United States. They're costly, oftentimes lives are lost. And it can be a bit confusing to know what the story is in terms of their relationship to climate change. And we've gathered together a couple scientists who have studied this in their day-to-day research programs and have can give us some perspective on how climate change relates to wildfire, how wildfire relates to climate change issues, and hopefully one of the things you'll be able to take away from today's conversation is enough of a background that you can sort of parse the claims that you see over the fire season that the United States is entering into. We hope this is a productive conversation. We're going to try and keep it relatively short on the front end and leave room for Q&A at the back. We invite you to use the Q&A function here in Zoom to offer your questions on a rolling basis, and the Niskanen Center staff and myself will moderate a Q&A at the end of the presentations. I also feel compelled to take a moment to acknowledge that this is a very difficult time for many people here in the United States and around the world, living both under the coronavirus as well as the upheavals that we've seen over the last few days. And if you will permit me, I'll take a moment to remember parts of the Niskanen Center mission, which I believe are very important. The Niskanen Center's mission is to promote policy change that will open society. And at the center, we believe that society should be open to political, cultural, and social change, open to free inquiry, open to individual autonomy, open to the poor and marginalized, open to commerce and trade, open to people who may wish to come or go, open to different beliefs and cultures, and open to the search for truth. It is for this last one that we gather today. And even as the forces of populism, closed-mindedness, and violence darken these days, we remember that the search for truth and the truths that science can offer us allow us to make better decisions and ground us in joint reality. As the politics of the 21st century will increasingly pit defenders of this open society against a new breed of populists, we are animated by our firm belief that science, empiricism, and a close examination of our own ideas will lead us to wiser choices. I thank our panelists for joining us today. We have Dr. Zach Zobel, who is a project scientist at the Woods Hole Research Center. His work focuses on climate modeling, extreme weather, and the socioeconomic effects of climate extremes. Zach recently led the Woods Hole Research Center contribution to a large and impactful report published by McKinsey & Company on the physical and socioeconomic risks associated with climate change over the next 30 years. One of those is the increased risk of wildfire. Professor Erin Hanan joins us from the University of Nevada in Reno, where she runs the Fire and Dry Ecosystem Lab. She's an ecosystem scientist and, in a way close to my heart, a biogeochemist. And her studies today, or the studies she's going to talk about today, focus on the interaction of wildfire, ecosystems, and climate change. We welcome them both, and we are glad that they are here to join us. To offer a little bit of perspective, I wanted to touch on a couple things. This is a photo of the aftermath of the Camp Fire, in particular which destroyed Paradise, California. It burned over 150,000 acres and led to the deaths of more than 80 people. It was started by a fallen power line and contributed to the bankruptcy of PG&E, but in the background of it was a hot and dry season. Earlier this year, 2020 having been as dynamic as it has been, it's easy to forget that this was this year. Bushfires in Australia burned in a remarkable way across much of that country, the evidence of which is visible here in satellite photography. 46 million acres burned, 34 dead from the direct impact of fire, and more from the secondary effects. When these fires were ongoing, Zach and I wrote a blog post for the Niskanen Center website trying to understand and parse the claims that were being made at the time about these fires. Here are two examples. At the time, the Washington Post the editorial board wrote that Australia's apocalyptic fires are a warning for the future. And in that piece, they explicitly related a changing climate to the horrific fires that were being witnessed at the time. And at the same time, the Wall Street Journal published commentary saying that attributing these bushfires exclusively to climate change was a gross oversimplification. These are the kinds of claims and counterclaims that I see pop up repeatedly during large wildfire events, and helping understand, what the thing we want to accomplish today is understanding how to parse them, how to know what is true, what is not, and what the real relationship between these things is. One gets the picture that we're living in an area of high cost fires and increasing fire activity. Here are two sources of data or information, both published by the federal government here in the United States. On the left, we see large damaging fire events as compiled by NOAA in its Weather and Climate Disaster database. And you see in descending order the large costs of firestorms and fire seasons. Many of these are located in California because this is metriced in cost. But you also see that many of the top or most damaging fires have occurred in the last decade. And in fact, I counted them, and 6 of the 10 largest wildfire events by damage have occurred in the last 10 years. And the top 5 years in terms of total acreage burned have all been in the 2000s. We also see on the right-hand side, total US area burned, and federal suppression spending. That's the money spent by in firefighting over the last 30 years. And there we see increasing trends in both, though there are large performing seasons or really bad seasons episodically in the past. And it's impossible to look at these signals and say, well, what about climate change? We know that climate change doesn't just start fires, but we also know that the weather that creates the conditions that favor fires can be associated with climate change in some places, or already has been. Those are high temperatures, low precipitation, low relative humidity, or high wind speed. And we see here on the right, the Interdepartmental Fire Center, or Interagency Fire Center, has already published its potential outlook for this year, and I've included here for visual interest July 2020. We see above normal fire conditions in their predictions for much of the Western United States. So when we consider, how climate change is affecting these underlying conditions, or when we start talking about wildfire in the context of climate change, it's by these mechanisms that we expect to see a lot of changes. Now, thankfully, Zach has done quite a bit of research on our understanding of these underlying drivers and how that has affected wildfire. I invite him to share his screen and discuss that for a little bit. And in particular, I think we want to know how are these effects changing, and how will they change in the future, and what Woods Hole research in this area looks like. Zach may still be muted.
Yes, I am. Can you guys see my screen?
Yeah, you're good. You're good for launch.
Okay, thanks. Hi guys, as just mentioned, I'm Zach Zobel from the Woods Hole Research Center. And today I thought it'd be a good idea to just do a quick case study that actually expands a little bit on what he just talked about. And we'll be focusing in Australia. And this case study is going to highlight how we are thinking about climate risk of wildfire going forward and the vulnerabilities that might be in place. So first I wanted to give some background information on what we're actually doing here. So around the world, there have been several different fire weather indices that have been developed. These indices are incorporate a large range of different atmospheric conditions, as well as vegetation type and land surface type. One of which is known as the Fire Weather Index, because scientists are very creative when they come up with names of indices. We'll call it FWI going forward. And it was developed in Canada. And it actually has been shown to perform very well globally, and even outperform metrics that were developed in the United States and Australia specifically for those climate regimes. And so that's why we chose the FWI index, so that we can compare regions around the world using a common indice, and we can see which areas we should be most concerned about for increasing fire risk. As Joseph mentioned, fire weather is dependent on a lot of different atmospheric variables, including vegetation type, which is a land surface variable. Some of those variables are drought, temperature, relative humidity, wind, all of what he mentioned. Drought is actually an important one here, because the temperature, relative humidity, and wind are important for the day of a potential wildfire outbreak, but there needs to be some kind of drought or dry period leading up to that day in order to really get a serious wildfire event going. Since wildfire can vary on small spatial scales, we use really high resolution climate models with data from state-of-the-art regional climate model output that have just been run in the last several years. However, the data used make predictions that would have been the same if we had these capabilities 15 years ago, meaning the underlying data has been around for 15 years. And that's actually going to be important when I talk about Australia and in the case study, and I show how accurate our models were at what would have been predicting 2020. Finally, in order to really get a good understanding of how FWI, how well it is predicting, or how efficient it is predicting a small wildfire event turning into a large event, we have to get some historical context. So we used historical observational satellite data to find an indice that sufficiently represents the majority of large fire events. And we looked for a fire regime or fire location that had a percent of detection of large fires of at least 70%, meaning 70% of the time there was a large fire, this index was sufficiently high that it would have predicted this event. And some of the regions that we found this to occur in are the Western United States, the Mediterranean Basin in Africa and Europe, Brazil, Canada, and the one I'm going to talk about today is Australia. So here is kind of the general output of what we view as wildfire risk. And what we're looking at here is the change in wildfire season. And what's important to note here is we're looking at the change in high fire risk days from 2021 to 2050 and how it compares to a reference period of 1971 to 2000. First and foremost, that reference period isn't a far away period. We remember the year 2000. We remember, most of us remember the mid-90s. And so we're also forecasting this for essentially starting this year going forward, the next 3 decades. And as I mentioned before, the underlying data that were used to run these high resolution new state-of-the-art models, actually that underlying data was developed about 15 years ago. And why that's important is one of the reasons I chose Australia for this case study. The fires in 2020 mostly started in this high fire risk area on the eastern 1/3 part of the continent. In that area, in that region, it says for the next 30 years, that specific area, there's supposed to be about 30 to 60 more days per year. That's what that color bar is representing, 30 to 60 more days per year when you get to orange or higher of high fire risk days. And so 2020 was kind of a textbook example of what this is predicting. The fires started in this regime here, and that's where they were initiated, and the wind blew them towards the coast. That's what actually makes Australia a very vulnerable continent. most of the central part of the continent is desert, very hot, dry climate. That desert and dry and hot air is actually expanding out into the edges of Australia. The edges of Australia is where all of the population of Australia lives. It's also a somewhat vegetation-rich regime, meaning these hot, dry conditions are moving into areas where there's adequate fuel for increasing fire weather risk. So those two things combined really made it so that 2020 kind of was a perfect storm, but it really wasn't, because the climate models have been predicting that these type of years are going to be more frequent and more intense in the future. And that was really what I wanted to focus on in Australia. I also showed the locations towards the end of the event of where the active fires were. And this was as of January 16th. This was well after the initial fire took place. And now they have spread to the coastal areas where a lot of the major population centers are. And this is also where there is a lot of vegetation. This is also happening in the United States. The United States has its own unique set of concerns. As the wildfire season lengthens in the United States, especially out west, the season extends into November and December. And why this is particularly concerning is one of the drivers of a small wildfire event into a large one is actually really high winds. And as we extend the wildfire season into this season, we extend it into the timing or the period of time in the year at which something known as the Santa Ana winds start to pick up. And we saw this actually occur and play out in front of our eyes in November of 2017 and 2018, where we had very rapidly increasing fires and fire size because of the very dry conditions, the ignition, the campfire being the example, and then the quick spread where it went all the way through the town of Paradise in about 20 minutes after it ignited. It was unbelievable how quickly it spread. And a lot of that was driven because these dry conditions are taking place later in the year when we have higher frequency of really strong and gusty winds. Humans actually in the United States cause a lot of the wildfires. It's usually done from human air. It's not done on purpose for the most part, but it's usually human air, flicking a cigarette, not putting out a campfire, no pun intended. And so we don't expect that part of the equation to really change as we go into the future. What we do really expect to change is the frequency of high fire risk days. And I'll end this brief little case study with a metaphor, and that is, if I were to give you a 6-sided dice and I were to say, you have 2 rolls and you lose if you roll a 3, you would probably take whatever amount of money I was offering you because the probabilities would be in your favor. Now, if I do the same thing and say you're now rolling the dice 4 times, and if you land on a 3, you lose, the odds are no longer in your favor. And that's what happens when you expand the wildfire season. The probability of human error will always be there. It will always be underlying in wildfire risk. There needs to be an ignition source. However, if the length of the season is longer, the likelihood for a large fire event to occur actually increases quite substantially. And so I'll pass it back off to Joseph.
I wish I wasn't so bad at Zoom. Thank you, Zach. It's a really interesting maps painted red. Like all things in science, the story is more complicated than just, we've created more days where fire weather is getting worse, right? Even though it seems like the ability of scientists to identify places where that is happening or will happen in the future is being refined. In particular, it seems like there are a lot of questions about, how our relationship to the land, both in terms of where people are living, but also in how, like, for instance, forests are managed, whether they are sufficiently raked, is a part of the equation. And thankfully, Dr. Heynen has focused some of her research on that, and we invited her in particular because I think she's one of the best, one of the leading people in trying to understand this relatively complex and nuanced relationship. Aaron, if you could take the mic and kind of give us some more perspective on how we should be thinking about land use, human interaction with the landscape, the ecosystems that are subject to fire, and their relationship to climate change, we would appreciate it. Taking the mic implies unmuting oneself.
Thanks. Can everyone see the screen okay?
Yeah, you're good to go.
Okay. First off, I just wanted to thank the Niskanen Center for hosting this and for the opportunity to come talk about my research. And I really appreciate everyone who signed in to listen. So basically, research in my lab focuses on how climate change and management activities influence wildfire regimes, mostly in the Western US, and then how changing fire regimes are going to affect ecosystem and watershed processes. And so especially things like carbon cycling and stream flow, or ecosystem services that we all depend upon. Also by wildfire regimes, what I'm referring to is the typical size, frequency, and severity of fires over a period of time. So characteristic fire behavior through time. So as was mentioned earlier, we've seen multiple catastrophic megafires over recent years, both in the US West and globally. And so this photo is from the 2013 Rim Fire, which was the largest fire ever recorded in the Sierra Nevada. And so as the frequency of these extreme fires increases, we really need to develop better strategies for managing risk. But the effectiveness of risk mitigation efforts is going to depend on why wildfire activity is increasing in the first place, and what factors are influencing fire behavior at the scale where management is actually implemented. So a question that pops up over and over again in the media and elsewhere is, are these megafires due to climate change, or are they due to forest mismanagement? And we hear a lot of conflicting opinions about this, and so the public is justifiably confused. And so I'm hoping I can help shed light on some of the complexity here today. So a spoiler is that it's both, and that the relative influence of these two drivers is going to vary depending on where you are. So also there's general scientific agreement that in forested systems, climate change and historical suppression are two key factors that enable ignitions to grow into megafires. But wildfires result from very complex interactions among climate, vegetation, or fuels, and humans. So historically, it's really difficult to attribute the individual role of any one of these drivers because they're interacting in multiple, very complex ways. So attribution is very challenging. See if I can, yep. So over the last decade, the scientific community has made a lot of progress in understanding climate-fire relationships. And this is in large part due to a global satellite-based record of fire activity. So at large scales, for example, across the entire Western US, we're beginning to see that there is a very clear link between climate warming and increases in burned area. So in this graph that I'm showing here, John Abatsoglu and Park Williams used this satellite data set that I just mentioned across the Western US to try to examine relationships between fuel aridity and the total area burned. And so the red dots in this figure are the most recent part of the record that they analyzed, so between the year 2000 and 2015. And that's where the climate change signal is going to be the strongest. And so you can see that as fuel aridity increases on, I'm not sure if you see my arrow, but on the x-axis, as fuel aridity increases, so does the amount of burned land. And in the more recent part of the record, so 2000 to 2015, the red dots, you tend to have the highest aridity and highest area burned. So basically, climate change is increasing fuel aridity and increasing the number of large fires. So even though these trends are becoming clearer at large scales, again, across the Western US or in regions, there's still a lot of debate over how climate change and historical fire suppression or mismanagement have contributed to the changes in fire activity that we've seen in specific regions and specific ecosystems. So we know, and we've known for a long time, that in more arid forests, such as the southwestern US ponderosa pine forest, extensive 20th century fire suppression has led to overstocked forests, accumulation of dead materials, and what we call ladder fuels, which basically take surface fires and can propagate them into the forest canopy, making them much larger and much more destructive. So these drier forests have historically burned at high frequency and low severity, basically typical surface fires. But these changes in forest structure that are pictured here have altered the natural fire regime. And so in these systems, fuel management, so fuel reduction treatments, including things like controlled burns and forest thinning, can help reduce the occurrence of catastrophic fires. But fuel treatments are expensive, and also fuel treatments can sometimes lead to unintended consequences. And so it's really important to know when and where fire activity is being controlled by fuels and how those relationships are modified by climate change. So that's where my research comes in. And in my lab, we use a variety of different approaches to understand interactions among climate change, fuels, fire behavior, and fire effects. And so today I am focusing on the simulation modeling work that I do. Excuse me, so specifically we're modeling how climate change and fuel accumulation that is due to historical fire suppression have promoted the spread of severe fires in the Western US. And more importantly, which one of these drivers dominates at the scale where management decisions are being made. So this is something that is not possible using observations alone, especially at management relevant scales. And this is because, as I mentioned before, fire results from so many different complex processes, and extreme fires are rare in any given location. So it's very difficult through observations to have the statistical power that would be necessary to say, to attribute anything. And so that's where models come in. So models allow us to vary one specific driver, turn a knob while holding everything else constant, and then being able to figure out, well, okay, what is the role of that particular driver? And so the modeling framework that I am working with is called RHESSys Fire. And so this framework couples a watershed scale hydrologic model, which is kind of shown here, with a model for fire spread and fire effects. And so I'm just giving a very brief overview of the model, but just know that it includes many different processes, and I just don't have time to discuss them all. But in general, the way it works is that the model takes climate inputs and feeds them into these process-based submodels that simulate vegetation, soil, and hydrologic processes across spatially complex terrain. And so this enables us to simulate the fuel development across a landscape or watershed, how that interacts with aridity, topography, and wind to influence fire spread. And then it models how the effects of fire feed back to influence future fires. And so we refer to this as a fire regime model because it's not just simulating one individual fire, which many of the tactical fire models that people are familiar with do. Instead, this is simulating fire characteristics over time. So I have been running model simulations both with and without historical anthropogenic climate change, and with and without 70 years of historical fire suppression, which I model as complete fire exclusion from the landscape, so the most extreme version of fire suppression. And then I'm examining how these two drivers have influenced fire regimes over the last 4 decades. And so in this figure, I'm just showing 2 example watersheds that are located in central Idaho. You can see these watersheds are relatively close together, but they have had almost opposite responses to climate change and fire suppression. So in the top panel, this is the wetter watershed, and you can see that there's a clear climate change signal that's distinct from the effects of fuel. So the climate change scenarios are shown here. And what I'm showing is with climate change, what is the difference in the probability of fire in any given location? And so if it's yellow, orange, red, that means the probability has increased. If it's blue, it's decreased. And so this is the effects of fire exclusion. And so you can see that, that climate change is increasing wildfire risk. And I'm not showing this data here, but we are finding that this is happening to the largest extent in wetter areas that have naturally high fuel loads but are generally less flammable. So climate change is drying them out and making them more flammable. In the more arid watershed at the bottom, climate change actually decreased fire risk in the southern portion of the watershed. And this particular area is extremely arid, and it contains not just forest, but a lot of sagebrush. And so this is at the far end of an aridity gradient, and it's not the typical forested or chaparral system where we're seeing a lot of the catastrophic megafires. This is an extremely fuel limited system. And so what's happening is climate change is decreasing primary production and therefore fuel loads. So in some parts of the watershed here, where you can see some of the oranges and yellows, you can see that fire suppression is also increasing fire risk by allowing fuels to accumulate. But this is only occurring at intermediate levels of aridity, where there's still enough moisture for the vegetation to grow and for fuel density to increase. So overall, what we're seeing is that local responses to climate change and to fire suppression are highly spatially variable. And so to be effective, fuel management practices should be evaluated within the context of local environmental conditions, including aridity gradients, which are influenced by climatological dryness and also by local topography and vegetation. And so there's no one-size-fits-all approach to fuel management. So coming back to the original question, is it climate change or is it forest management? So fire regimes in general exist along an aridity gradient. And so they range from being limited by flammability. So that would be this example from the Pacific Northwest Cascade Range. And I'm kind of putting the absurd examples here. So this is a system that is old growth, has tons of fuel on the landscape, but it's really wet, and so it's extremely unlikely to burn. At the other extreme here, we have the Colorado Desert. The climate conditions are almost always conducive to fire, but there's not enough vegetation growth or fuel on the landscape to propagate fire. And so most forested systems are going to exist somewhere in the middle. And so climate change and fire suppression are going to affect those systems differently depending on where you are along that gradient. And so, again, what we're seeing is that variability can, or those things can vary at very fine scales. So, you know, there are differences in north versus south facing slopes, or with elevation, or with vegetation. And so kind of the last thing I wanted to note is that in many of the forested systems that are considered overgrown, many of these are semi-arid, and so the materials that need to be removed to reduce fire risk aren't actually valuable as timber in many cases. So in many of these systems, prescribed fire or sometimes thinning is the most beneficial and cost-effective solution. But these treatments are costly, and so it's important to know when and where they're going to be most effective. Thanks.
Awesome. We've had a few questions come in, but our, you know, if our attendees have any burning questions, they may submit them in the box or in the chat, and we will try to get to a few of them. I'll take moderator's privilege, however, and ask Aaron first. You know, if we can approach this from a binary standpoint, right? Climate change or land management, climate change or human behavior. When you kind of dial up to the highest levels, what is your, you know, grounded in your experience, what is your general sense on how we should think about the relative roles of these two things going on? I mean, right? So there's a lot of things that could be done to reduce the pace or severity of climate change this century, but that aren't going to change the pace or the severity of climate change over the next few decades. And so, how do you think about the relationship of management and a changing relationship to wildlands, but not really wildlands, to large forested areas, perhaps, in the context of these sort of two different ways of affecting the risk curve?
Yeah, thanks. So as we know, it takes a combination of factors to produce destructive fires. And this is a really complex question because the way those combinations of factors interacts is different everywhere. And so in addition to climate change, which we know is an issue and we know we need to aggressively reduce greenhouse gas emissions, there are other sort of human factors that are changing fire. So as we've mentioned, historical fire suppression and increases in forest density, or developing human communities in areas that are extremely fire prone or are becoming increasingly more fire prone. So these factors we know in some places are magnifying one another, but often there are different factors that are going to dominate in different locations. And so being able to identify what is the dominant factor, because if you are in a relatively humid, dense forest, climate change is going to be the major driver increasing fire risk because you are going to always have the fuels there to burn. If you are in a sort of semi-arid forest where there's enough moisture for fuel to accumulate, but it's also fairly dry and so it historically burned frequently, if fire has been being suppressed there, then we know that fuels might be accumulating, and going in and doing fuel reduction treatments can be beneficial. These are expensive. There's not often an incentive to do so. And so I think through modeling and through research, we need to try to better understand, like, where can we target these management units to be the most effective.
Interesting. Particularly interesting that your comment to me about, and one of the things I learned, that a lot of this management task is not actually just forestry and harvesting, right? Or there's not necessarily an economic reason to do that anyway. It's probably going to have to be active in some way. Zach, Aaron kind of hinted to this, but I know that your work has looked at it expressly, that a lot of the increasing risk profile also comes from human expansion into what is, in the terminology, the urban wildland interface, right? Moving domiciles and buildings into places where they're going to be exposed to land that may burn. Can you kind of describe for us some of the issues at play, some of the potential socioeconomic implications as we think about ways to reduce these risks going forward?
Yeah, sure. So really the fundamental problem, and it's not really a problem, but the fundamental human behavior that's taking place out west is almost a deurbanization. People are moving away from cities and into forested areas that have already had historically a high fire risk regime. They're also moving into areas that fire suppression makes fire suppression more challenging, because you are at risk of a fire growing out of control and entering into populated areas if you do controlled burns, is what they're called. And so from the 1990s to the 2010s, I think there was about a 40% increase in all Western states and just the amount of population living in the wild urban land interface. So that is a rather substantial amount of people that have now moved into at-risk fire regimes. And so this actually compounds the effect of climate change. And you spoke of the damage estimates that are taking place, which sometimes can be misleading in the opposite direction of climate change because of this fact. You simply have more assets living in at-risk fire areas. And so, yes, you expect wildfire size and intensity and spread to increase, but you don't, it's not the whole part of the equation. You have to factor in human behavior in moving into these areas. And I also spoke about the ignition source. With more people living in this area, the likelihood of a mistake being made, and most of the time they're not intentional, a mistake being made in providing that source of ignition that kick off a relatively large fire, that obviously increases as people are spending more time in these fire regimes.
Aaron, there's been a question for clarification on one of your slides, on one of the slides showing the two watersheds and the relative role of climate change and fire suppression. Mm-hmm. It appears that there is some places where fire suppression has decreased or increased fire risk. Can you kind of explain what you mean by that and what may be going on?
Yeah, that's a great question. So in the wetter watershed, this was a really surprising result. We found that historical fire suppression actually decreased fire risk, which is the opposite of what we would think would happen. But what's happening there's a couple things. So we suppressed fire in the model for 70 years, and then we allowed fire to return to the landscape. And so early on in the simulations, we had some very severe fires which consumed fuels. And because fire is a self-limiting process, so the fire spread through the landscape, consumed the fuels, and it took a long time for those fuel loads to recover. Ultimately, over the entire 40-year simulation period, there was a reduction in actual fire. In addition to that, another thing that seems to be happening is that with fire suppression in this wetter area, we get this growth of the overstory canopy and closing of the canopy, which is maintaining more humid conditions beneath at the ground surface where the fire is spreading. And so because of that, it's reducing fire risk in that particular watershed, which is mostly flammability limited. In another system so systems tend to be either flammability limited or fuel limited. In a fuel limited system, you probably wouldn't see those sorts of effects, but because that particular watershed, Johnson Creek, is a flammability limited system, the shading and sort of humid microclimate created by the overstory canopy was limiting fire spread.
That is super cool.
Yeah.
I have so many follow-up questions. I think, I'll ask one. How unique are the conditions, do you think, in that particular area, or do you have a sense of how unique they are compared to what, how widespread, if you actually wanted to create an adaptive or a sort of system smart approach to fire management?
Yeah, so these are very spatially complex landscapes, and each one is behaving a little differently because of a lot of different interactions between things like snowpack, vegetation cover, local gradients and topography, aridity, and fire behavior. And so we are able to simulate a lot of those things with a modeling framework. And what we have begun to pull out from this is that there are these thresholds that seem to appear over and over again. So in areas where soil moisture is extremely low, climate change is going to reduce fire risk because things become so fuel limited. On the other hand, in places where soil moisture is extremely high, climate change has a big effect on increasing fire risk because it is increasing sort of aridity and flammability conditions. Then there seems to be this sort of intermediate aridity zone where it is influenced by all these other local conditions. So we had one watershed that had very high elevations, and a lot of the wetter areas were mostly covered in snow for most of the year. And so those areas didn't respond in the same way to climate change as the lower elevation areas that have the same moisture. And so what we're doing here is kind of presenting a framework for trying to disentangle and tease apart these drivers at fine scales. But what we see in one watershed is not necessarily applicable directly to another. Though we are seeing these general patterns, and aridity seems to be the major factor influencing that. And so climate change is something that is influencing fire behavior regardless of what system you're in. It's just influencing it in different ways.
Super interesting. What the questions coming through, one of the ones that we hear most often when we're talking about science and as it relates to public policy is, okay, what do we do? Right? Policymakers have people bringing them problems and risks all the time. In your judgment, informed by your research and your experience in this area, how do you respond? What do you say to somebody who says, okay, great, now what do I do? What would be your key recommendations? What would be the first places you think they should look? Question offered first to Aaron and then to Zach.
That's a really tough question. Policy and science are happening on different timescales, and people, I think, look to science for solutions to policy questions. And I think that policy should be informed by science, but there are times where decisions have to be made in the face of uncertainty, and sometimes very large uncertainty. And so I think that we need sort of a multi-pronged approach to dealing with fire risk. And one of the things is to aggressively reduce greenhouse gas emissions. But in addition to that, fuel treatments and trying to develop ways that people can live with fire is also crucial. And there are a lot of managers who have tons of experience and just like knowledge from doing these fuel treatments on the ground and how things have responded over time. And so we need to rely on them to help us make decisions in the face of uncertainty. There will always be uncertainty in models, and the way science works is we slowly sort of try to narrow that uncertainty, and then it's up to policymakers to consider that and make decisions.
Yeah, I thought that was a really concise and good answer, especially about the mitigation aspect. I'll speak a little more on what we can do to adapt to the already present risk. First and foremost, as you would probably guess, as fire risk increases, that just increases the market for fire-resistant roofs and structures. That's a way to adapt short-term to help soften the cost. And all of the techniques that Aaron spoke of earlier also apply on a local property scale. You can do things around your individual properties that help keep the fire at bay as it approaches your house, essentially. Reducing the fuel and whatnot in those circumstances. Something I've actually experienced that I think is a more and more growing concern is what's happening in the insurance market. And that is something that actually can take on a big brunt of the climate change burden, but to a certain extent. And so what's happened in California in the past year is government regulators have had to come in and stop the insurance companies' tendency to increase rates in these fire risk areas. They're doing this because they grossly underestimated the rapid expansion of large fire events, specifically in California. And so they're trying to compensate for that after 2017 and 2018 by increasing the rates, and government regulators had to come in and say, and put a stop to it. Well, what that's actually doing, and what's actually it's actually causing a bigger problem, because insurance companies are trying to get out of the market altogether, to the point where some properties or some areas in California can't get insurance when it comes to wildfire risk, because the risk is too high. Insurance companies at times just won't even take a call. This is a big problem for elderly or poorer communities who can't easily relocate and live in these increasing fire risk areas. Paradise, California would be an example of a community like that.
We're running up on our allotted time. We got a late start because of some settings issues. So if we go a couple minutes over, I'm fine. But before we do, I invite our attendees to offer a virtual round of applause, and we really appreciate both of you being here today. If I can ask kind of one final question to play us out, and this is to both of you. You know, we often talk about wildfire in the context of human lives lost and property damage, both of which are incredibly important things. But it's not like there aren't you know, other processes going on in forests, biogeochemistry.
Destructive, it's pushing a system outside of its range of natural variability. And in addition, a lot of these ecosystems provide services to humans, so clean drinking water, water quantity, water quality. Fire can release a lot of materials that end up in streams and watersheds. And so in California, a lot of these chaparral systems that burn are burning near reservoirs or drinking water supply. And resource managers and residents justifiably become very concerned that this is going to devastate their local drinking water supply. So there are, I could go on for a long time listing all of the different concerns. But it's, yeah, it's typically something that changes the fire regime or pushes a system outside of its natural variability. Those are the things that we need to be most concerned about.
Yes.
Okay, may I ask a second question?
Oh, sure.
Oh my gosh, I'm so interested. You know, one of the things we read about happening under climate change is significant shifts in biome, right, or in ecosystem function as the climatological envelope changes, right? So in a particular place that's been used to a certain envelope of temperature and precipitation, as it moves out of that envelope, you may get a, you know, the classic image I have in my head is, you know, the landscape from 100 miles to the south just kind of migrates up over time. Not the hills, but the plants and the animals or whatever. Is fire a symptom of that? Right? Is that that's not a smooth process necessarily. I've always kind of wondered that. It's an open-ended question. If you don't have the answer, that's okay. But I've always wondered if you know, the process by which that occurs kind of looks like these large singular events versus a sort of steady replacement.
It's, you know, fire is sort of something that is feeding back to both influence and be influenced by that process. And so if you have a shift in vegetation, you'll almost certainly change the fire regime. And then as if you have a massive fire that clears the vegetation, that might clear ground for new species to come in. And so as the climate is warming and vegetation is shifting, then certainly fire regimes are shifting as well.
Very interesting. Yeah, thank you for your research and presenting it to us. It's really rewarding to hear about it. Zach, have you got anything to add on these secondary considerations or other considerations?
Yeah, I'll just conclude with one final remark. So the thing that I think about a lot, which isn't factored into a lot of our scenario analysis going forward, is the increasing frequency of wildfires in the Arctic. And 2019 would be a perfect example of just large wildfire events that run uncontrolled for a while. And not only does that release a lot of CO2 and feedback into climate change, but something that our research center is actively researching, and something that's almost more concerning, is the release of methane as permafrost thaws underneath the ground due to these wildfires. And it's something I think a lot about, and when I see these events pop up on the news, because it always makes a good headline, the Arctic's on fire. What I think about and what I think more people should think about is just the rapid acceleration of greenhouse gases that have been trapped in the Arctic for centuries that are now being released because of these large wildfire events. It's an active area of research, and it's something our research center is working hard to try to quantify.
Yeah, so I totally agree. I mean, I feel bad. We've had this U.S. focus. I think that, you know, given our audience, that's important, and given that we're going into a new fire season. But it seems like we could have a whole second session on Arctic and tropical forests and the and the dynamics at play with fire and climate change in those contexts. To our attendees, if you want to see that, a really good way to let me know and to let our staff know would be to reach out to me on Twitter or via email and offer commentaries to that effect, right? That we want to see more of this kind of discussion. We'd like to see a second episode on tropical and Arctic fires. As well, a really good way to show appreciation to Zach and to Aaron would be to follow them on social media, keep track of their work. They're both doing really important research on how we think about climate risk in over the next few decades and how we can work to manage it. I thank them for joining us today. And with that, I think we will close this conversation. We appreciate your attendance and your attention. We hope I hope that you've taken as much from it as I have, and we wish everyone a healthy and safe rest of the work week, and we will see you the next time. Thank you all.